Hi, this is Mrs. Gorley, and this is the BC Calculus Lesson 10.1 on the parametric equations. So why do we even need parametric equations? Do you guys know what they are? You ever heard of them?
They're equations.
They are equations. They have an equal sign in them. Does anybody know what it is? You've seen that, heard that? Well, it has to do with a parameter. And a parameter is another piece of information that you're going to introduce that kind of controls the equations in a way. So like for instance, look at the elliptical orbits here. Now, have you guys ever done conics where you've actually come up with equations of ellipses before? Well, I'll just tell you really quick kind of what it is. If you have something like, say, x squared plus y squared, say, equals 5, or let's make it easy, equals 16. Do you know what that's the equation of? A circle. And where is it centered? 0, 0, 0. And what's its radius? 4. It's the square root of that. So what if I change it to x minus 2 squared plus y plus 1 squared equals 16? Now what's the center? Yeah, it's the opposite of these. It's 2, negative 1, but it still has a radius of 4. Okay, so that is a circle. Now, another way to write this circle like this one over here would be if I divided both sides by 16. That's like dividing each term by 16. This is another way to write the equation of a circle where this side over here becomes 1. And you see that radius is now under each number, divided under each number. Well, this is actually the form of also an ellipse. The difference is the numbers here are different. So, like let's say this one is 9. That means on the x-axis from the center here, you would go 4 units, square root of 16, or 4 units away for a point on the ellipse. But on the y-axis, you'd only go 3 units away, square root of 9. So that's what makes it kind of elliptical, like an oval instead of a nice circle. Okay, so that is ellipse. So knowing those, and of course if you do this kind of thing on it too, in place of the x and the y, if you have x minus 2 squared and whatever, it shifts it instead of being centered on the origin. So that's just basically a circle and an ellipse. There's also hyperbola. If you want, it is nice if you know these equations because they come up every once in a while on things, and it used to be in the pre-calculus core, which was basically your secondary 3 now. It used to be in that core, but they took it out of the core, and it is nice to have it when you go up into higher mathematics. So if I was you, I would just Google like conics, or if you want to use one of my old books, I have my old books over here in section 10.1 has a brief discussion about all the different conics. Basically, it's called conics because if you take a cone and you slice a cone, if you slice it straight across, you'll get the slice shape is like, think of like a piece of cheese getting sliced right there. That would be the slate shape of a circle. But what if I go at an angle here instead? What would the slice look like then? An oval, yeah. And if you go straight down, you get a parabola. And if you have 2 cones like this, inverted, and you go straight down between both of them, or even a little bit tilted through them, you get what's called a hyperbola, where it's basically 2 parabolas, one going one way and one going the other way. So if you wanted to look that up, it would be helpful for your future in mathematics and other higher level classes and stuff. I would look up conics. And it does help because it helps when you see that, you know that, like that, when you see it, you know that that's an ellipse. Okay. The hyperbola is very similar to this, except for it has a negative sign in between them instead of a positive. That's what flips it going out instead of in to make the oval. Okay, so that being said, we could come up with equations. Let me get rid of all this. We could come up with equations for our ellipses here, right? For all of these elliptical orbits. But what else would be nice to know for an ellipse besides just an equation? For like in this, in case of the planets and stuff. What else would you want to know? Yeah. How fast they move around, yeah. And yeah, whether they're inhabitable. That's a whole different discussion. but yeah, you'd want to know that. Does it matter the direction they go? Wouldn't you want to know that too? Like what direction are they going around the sun and how fast they're moving? All of those things are important, not just the equation of the ellipse. So if we only have a rectangular coordinate plane where we come up with that equation, you know, like we had the x squared and the y squared thing on there, yeah, we can see where it's at in relationship to the sun there, but we don't know anything about the time or the direction, anything like that. Well, that's where the parameter comes in and is helpful. So the parameter in this case, if I was talking about these things here, would be time. I would want to know how long it takes for them to go around. So I would introduce time into the equation. And then I would also, while I'm doing that, I would want that orientation of what direction it's actually moving. Okay, so that's why we have elliptical or parametric rather equations. It doesn't have to be time that is the parameter. You can have like an angle be a parameter. You can have different things depending on the situation. You'll see an angle one coming up in the lesson here a little bit too.
You know, I was thinking that parametric equations had to do with Europeans falling from the sky.
I'm not quite sure why. Okay, I don't even want to go there. I don't know why. Okay, you can explain that to me later, Janir. All right, so let's look at example 1 here. So when you're given a parametric equation, instead of given one equation with just x and y, you're given an equation for x and an equation for y, and they both have the parameter in it. In this case, they call it t. A lot of times they call it t because time is a lot of times the parameter. So they call it t here. So all we do is we just take some values of t. Now it tells us in this case here that t goes from -3 to 2. So those are the values I want to plot on my little chart here. So I'm going to put across the t. So put -3, -2, -1, 0, 1, and 2. You get enough points in there to represent the graph. Okay, and then all we do is we take each one of those t values and plug it into the x and into the y to get our xy coordinate there. So when I plug -3 into the x equation, what do I get for x? 4, yeah. When I plug -3 in here, obviously we get -3/2. So there's the first point. This point, 4 and -3/2. So go over to your graph and go to 4 and -3/2 and put that first point on the graph. Okay, so I'll give you a minute to go through and do each of these and put all of the points on the graph. All right, those of you, if you're watching this at home, pause the video and do that and then turn it back on when you're done. Okay, so this is what you should have on your paper. Now, when you connect these, obviously it looks like it's making kind of a parabola shape here, right, to the side. But you want to connect them in the order that you did the points. So we always go from smallest to largest, like we have here, from -3 to 2. So we want these points going from this point and then this point last. So going from there to there, that's how we want to connect them. So we're going to start here. And you might think, what difference does it make how you connect them? It really doesn't. I mean, I could start at this one and draw. But what makes a difference is how I draw little arrows on it to show the direction. So we start with we draw our little thing there. That's not a very good one. Let me fix it a little. There we go. Okay, and then you put these little arrows on it to show the orientation or the direction that you drew it. So it's like that. You really only need just one arrow. I like to put more just because I'm weird, but you have to put at least one arrow on there somewhere to show what direction this line is being drawn from. All right, so that's what you guys have in yours. So now, on another piece of paper, or just right below that chart, I want you to make these equations here. And the same chart. This time our t is going from -3/2 to 1. And I still have, 6 points there. So I think if we go up by halves, we could get them all in there. So we'll say -3/2 for t, -1, -1/2, 0, 1/2, and 1. That gives us 6 points there. Go ahead and plug all of those into these two equations and plot those points. Okay, if you're watching this at home, pause the video and do that. All right, so what do you notice about the two things? Yeah, they're exactly the same. Did they look the same to start with? They looked a little different, right? The t values and the equations for x and y were a little different, but we ended up getting the exact same thing. And the graph looks exactly the same. So what is the difference between these two? Because they are different in a small way here.
One's an Indian and one's an African American.
No, that's not it. How are they different?
One of them, the bottom one, it goes to 0 at the top rather than stopping at -1.
Oh, I was supposed to stop there.
Oh.
Thanks for catching that. That's just
Me
a,
thinking I was
that's
being
just a
smart is just
mistake
a
on my
correct
part. Okay, now they look the same. Sorry. Thanks. But there's something else that's different. What do you think?
The range, like the -3 and
Exactly. Look at the time. If you thought of this as maybe seconds or something, this one took 5 seconds, whereas this one took 2.5 seconds down there. So the speed is the difference there. If I had just graphed this and you were just looking at the graph, you wouldn't know that without having the parametric equations on there. Okay, so that's that idea of how long did it take to travel, and then obviously our direction we got from this to where you would not get that from a basic rectangular equation. So again, before we move on to the next question, what would the rectangular equation be for this? If you had just wanted to graph this, how would you graph it? Well, when you're trying to convert to a rectangular form, these are the steps you do. The first thing you do is you just solve one equation for t, either one, and then substitute it in, sub that into the other equation. That will eliminate the t. It's called eliminating the parameter. Okay, eliminate the parameter. Or get rid of the t in this case. Okay, eliminate the parameter. So up here on this case, which one would be easier? We'll come up here and use it from our original problem here. These two up here. Which one would be easier to solve for t? Yeah, y. So let's take that y equals t over 2, solve it for t, and we get t equals 2y. So now take that 2y for t and plug it into the other equation for that t. So we're just using substitution. So we get 4y squared minus 5. So now you can see I have an equation with just x's and y's. That's an acceptable equation. It's not solved for y, but it is acceptable. In fact, I kind of like it because it tells me, because it's an x and a y squared, I know it's a parabola facing sideways instead of up and down, which is what we have on our picture here. The only thing that I would want to do is I would want to somehow restrict it so that I'm only going in this direction. So I only want to go from here to here on each one of these, doesn't matter which picture up there. From negative, looks like our lowest point down here would be at -3/2, and our highest point up here would be at 1. So those are the y values. I want y to be greater than or equal to -3/2 and less than or equal to 1. And that would give me that parabola within that, just that part of it. I wouldn't want to do it with restricting the x's, because if I said I want only x's from here to here, from -5 to +4, can you see a problem with that?
The top one will go to...
Yeah, exactly. This one stops right here. It doesn't have this part of the graph, so you'd be in trouble with saying that. So this one I would show the restriction on how much the graph I want to draw based on the y's, not the x's there. And you could solve that for y if you want. Be careful, if you did solve it for y, you'd have to have the plus or minus on it, on there, you know, when you do the square root on there. Okay, so that being said, let's move on to example 2 then. It says change the following to rectangular form by eliminating the parameter and then graph it. So change it to rectangular. What should we do then? What was our first step?
close multiplication.
Yeah, solve one of them for t. Which one would be easier to solve for t, x or y?
X.
Yeah, because y has two t's in it. That would be much harder to solve for t. And if you even can, I don't even know, we haven't looked at it, but I would use this one. It's got just one t value there. So if we solve that for t, basically if I multiply both sides by that denominator, I'll end up with this, right? And then I could divide by x on both sides. Then we could square it. To get rid of that square root, and then subtract 1. So t equals 1 over x squared minus 1. There's our first part. Okay? And then what's our second step? What do we do now with this t value? With the one, there you go, plug it in. So plug it in for each one of the other t's here. So y is equal to 1 over x squared minus 1 over 1 over x squared minus 1 plus 1. Well, that worked out nice. The minus 1 plus 1 is gone, right? Those are gone. So I end up with, let's see, we can invert and multiply here now since we just have 1 over x squared in the denominator. So here's our numerator, and then flip the denominator and multiply. So we end up with y is equal to 1 minus x squared. Right? You guys all get that? Okay, so it's a little, I mean, we know how to graph this. That's an x squared graph, and what direction is it going? Down, and where is it shifted? Up 1, yeah. So it's just this graph here, so we can put it on there. But should I be doing this entire graph? Should I be doing all of that? Well, look back over here. It looks like there's no domain restriction on this, the way that we have it written like that. But you have to think about before you simplified it. So up here, when I plugged it in, or even back over here on this value of t, is there anything you could not plug in for x? Yeah, you can't plug in 0, right? So I know 0 is not in the domain. And then think about this. If t, here, this is really important. If t starts with -1, if you plug a -1 in there, that's that value at 0 there. So it's got to be things bigger than -1. So which side of this graph should we be plugging in then? Well, think about it. If you go back over here and you say, well, actually right up at the beginning, up on this one, let me see here. Get my little highlighter. Look at that guy right there. Okay, if you plug in just values greater than -1, what is x always going to be? It's going to be what?
Greater than 1.
Greater than, is it 1? Greater than 0, yeah. Because I could plug in, like, if I plug in -1.2 or something like that, I'll just have a number number that's greater than 1. So any number, any value of t greater than -1 gives us a value of x greater than 0. So we actually don't want all of this graph over here. I don't even want this side at all. And I don't want this. This one's got to be an open dot here. So the graph actually looks like this with an open dot there because I can't plug in 0. And then I just want this right side. So this equation is good, but only with a domain of x is greater than 0. That has to be included with it, or else we don't have it done correctly. All right? If this had just said x cannot, or t cannot equal -1, and it said all the other values on there, could you have done it then? Could t equal things that are less than -1, the way that we have it? No, you got to square root of a negative then. So, yeah, even if it had said just t cannot equal -1, just the natural parameter of it, even without that said, we should have been able to figure that out because we have that square root in the denominator there. But it's nice that they gave it to us. Okay, so we've done what they said. However, what if they had said, Oh, by the way, let's see. How do we restrict the domain? We already talked about that. Okay. What if they had said then, now tell me the orientation? In other words, the direction. Orientation is that which way should we draw the arrows on it? Can you get it from what we've done here? What do you think? Can you get orientation, the direction, from the rectangular equation? What would you have to do if you want to get the orientation or the direction? It's the only way to do it. What did we do on the first ones?
Plug in a couple points.
Yeah, plug in some t values. You know that t has to start someplace greater than -1. So I would start by, if you just had like a chart of t's, x's, and y's here, and plug in some values. Now, I can't really plug in -1, but I could do the limit as x goes to -1 of the x function, or t rather, sorry, as t goes to -1. As t goes to -1 of 1 over square root of t plus 1, what would that go to? You plug in something really close to -1 there, just to the right of -1. I actually should say coming from the right there. What would this go to? Infinity, yeah, because it makes the denominator really, really small, which makes this go to infinity. Okay, what about the y-coordinate? The limit as t goes to -1 from the right of t over t plus 1. What's that go to? What do you think? Negative infinity, yeah, because the bottom, again, is very, very small, but then you're putting a negative on the top there, so it's going to be a negative infinity. It'll be a positive on the top, negative on the bottom. So that tells us this part right, where? Right here. This part down here that's going down to, as x goes to the right, so this is saying as x goes to the right, y goes down. That's what this is saying, going right and down. Okay, that end part. Let's do another point. What if we plugged in, say, 0? What do you get when you plug in 0? What's the x? 1. And what's the y? 0. So that's this point right here, 1, 0. So it was going this direction. What's really weird is all the numbers from where t was between -1 and 0 gave us this section up here. That's really weird to look at. Let me write that a little bit more clear. This was -1 to 0, all those values. And then this is the point right there when t equals 0. That gave us that point right there. So that means that this part has got to be the rest of it. That's got to be all the numbers as when t is greater than 0. Which is really weird to think that that little teeny spot has got all the numbers when t is greater than 0. But if you think about it, if you plug in like 1, you get 1 over square root of 2, which is about 0.7, and it goes on, and you plug in it here, you get a half. If you plug in a 2 for t into both of them, you get like about 0.57. It's 1 over square root of 3, and you get 2/3. So those points are on this part of the graph up here. They're on that part of the graph. And then if you go out to infinity, you're basically doing the limit as t goes to infinity of 1 over square root of t plus 1. Well, what does that go to? If you put huge, huge numbers in the denominator, where's this going to? Yeah, 0. Well, that's this point right here. That's when x equals 0. And the same thing here, if I do the limit as t goes to infinity of t over t plus 1, what's this one go to? 1, yeah. It's the horizontal asymptote of that equation there would be 1. Well, that's that point, 0, 1, the one that we get infinitely close to but never actually touch. It's really strange. So you got to have those arrows. If I wanted orientation, I have to do parametric if I want orientation. I've got to do that with some points. This one was really weird. People, you would assume that it would have been going the other way, but it's not. So don't assume anything. Always actually test the orientation if they ask you to test it. Okay.
Assume orientation. Okay.
Okay, don't even go there. Don't even go there, Sneer. Okay, so you know what? You are forever immortalized because I say things like that a lot in these videos, and these are the ones that I'm keeping. So funny. Everybody's going to know who Sneer is forever now. That's awesome. Okay, let's look at example 3. Eliminate the parameter to sketch the curve. All right, it doesn't say we have to do orientation on it, so let's don't to start with. And like I said, if you want to know more about conics, if you want one of my old calculus books that's here at section 10.1, or you could just Google conics and get probably a million lessons on it. So, conic equations. All right, so let's do this. Eliminate the parameter. Wow. What were our steps? What should we do for our steps? Okay, well, let's do y. Oh, no, let's do x. It's a little easier because it doesn't have a 3. So if I solve this for theta, this time the angle is the parameter, okay? So how would you solve that for theta? How do you undo cosine? Arc cosine, yeah. So it's the arc cosine of x is equal to theta, and then we plug that in here for that theta right there. So y is equal to 3 sine of arc cosine of x. Now we've got our equation with just x and y, but that is not an algebraic equation. It's got transcendental functions in it, and so we would really kind of want to figure this out a little bit. So if you think about it, if theta, back over here, we'll make a right triangle here and say theta, because remember we can do SOHCAHTOA with sine, cosine, and tangent. So if I just think about this right there, the cosine of theta is equal to x, or x over 1. Well, that would be, remember, cosine of an angle is equal to the adjacent side over the hypotenuse. So I could, from this angle, go the adjacent side is x over the hypotenuse is 1. And then I could solve for this other side here using Pythagorean's theorem. And so if you use Pythagorean's theorem, you get 1 minus x squared over here. Once I have that, then I could look at that angle then and go, what is the arc cosine? And I could actually solve this equation using all that. It ends up giving you an ellipse. But isn't that kind of long and ugly? You want to see a faster way? I'm going to show you a faster way. Get rid of all that, because it's just way too long. We don't want to deal with that, right? So, do you remember the Pythagorean identity with sine and cosine? What's the Pythagorean identity with sine and cosine?
Sine squared plus cosine squared.
There you go. Sine squared of theta plus cosine squared of theta is equal to 1. Well, how about we just plug in what these are? We know that cosine of theta is x. So in place of that cosine there squared, I'm just going to say, oh, that's x squared. Okay, what would I put in place of the sine here for the sine? I've got y equals 3 sine of theta. What does sine of theta equal then? Is it, well, what do you do first to just solve this for theta? Or for sine, sorry, sine of theta. Yeah, divide by 3. So it's y over 3. So in place of the sine right here, I could put y over 3 and squared. And it equals 1. Okay, so instead of going through that whole thing with the arc cosine and all of that kind of stuff, this is a really nice little shortcut. So remember your Pythagorean identities for trig functions, and it'll save you a ton of time and effort on here. This is just y squared over 9 plus x squared equals 1. So remember, we said this is an ellipse, so this x is like over 1 here. The square root of 9 is 3, and square root of 1 is just 1. So that's our distance on the x and the y coordinate. So on the y coordinate, because the 3 squared is underneath the y coordinate, that goes on the y-axis. This is centered at 0, 0 because there's nothing added or subtracted to the x and y coordinates on the top of these here. It doesn't have like a in here like an x minus 2 squared or something like that. And so it's centered at 0, and then from that center right there, we just go up 3 and down 3 to get our y coordinates, or our coordinates on the y-axis, and then we go over 1 to the left and right of the center to get our kind of our width of that ellipse. And then we'll draw our graph. So it makes this nice little ellipse, and you know it's an ellipse just because we've talked about then that just this one thing in conics. Okay, so we'll draw our ellipse. Okay, mine's kind of lopsided a little, but it's okay. Now again, if I wanted direction on this, if they said sketch the curve and then they said what's the orientation, what would you do?
Start plugging in some points.
Right. What point would you start with?
0.
Yeah, with theta equals 0. Orientation. I would make like a chart, however you want to do it. I could just do it up and down like theta, x, and y. And I'd start with 0 because it tells us we're going from 0 to 2 pi. I would plug in all the nice easy ones because we're plugging these into cosine and sine. So I would do like all of these, just the ones that are super fast. And then 2 pi is the last one. You don't even need to do all of them if you don't want to, because you just have to get direction on this. It turns out you're plugging these into this right here, into these two, into those parametric equations. So I plug it in, I plug in 0, I get the cosine of 0 is 1, 3 times the sine of 0 is 0. Just go through each one of them. And we get these values here, which are values that have to be on this curve up here we have, and they are. You can see our first one was right here. Our second one was there, and it goes all the way around and lands back where it started here. So our orientation is like this. It goes up from that spot and down like that. Okay.
Is it possible for the direction to change?
Not on a particular parametric equation. No, if you're given one, it's never going to change. I mean, they can give you other things on here, and then it could change, but they'd have to change the whole problem to make it do that. Okay, all right. Let me see 5 to 0. Can you do these parametric equations? Can you graph them and see the orientation and all that kind of stuff? Let me see everybody 5 to 0. Where are we at? Okay. That was all of that stuff that we just learned used to be, like I said, in the pre-calculus core. This is the calculus part, the next part here, is we want to talk about the rates that things are changing and the concavity and things like that. So we want to talk about derivatives and second derivatives on here. But I don't want to have to change every parametric equations, the pair of them, into rectangular in order to do the derivatives or second derivatives. I want to be able to do them from the parametric equations. It'll be a lot faster if I could do that, right? So that's what these are. This is, if you want to do the derivative, you want dy dx. So it says find dy dx, but you're given two parametric equations. You don't have an equation with just x and y in it. Instead of doing that, you can think, oh, well, isn't just dy dx is dy dt over dx dt? If you started with that, dy dt over dx dt, I could flip this bottom, if you think of them as fractions, I can flip this bottom one upside down and multiply, those cancel, and I just get dy dx, right? So it's just the derivative of y with respect to t over the derivative of x with respect to t, and you simplify them. Okay, it gives you dy dx. Okay, so let's, there's also, the second derivative is the one that most people make mistakes on if they're going to make a mistake anywhere. It's the second derivative. Because you would think then that you could just take the first derivative and take its derivative and have the second derivative. But it's not quite that simple, and it has to do with notation. here's like a simple version of it. If you want to look at my book over there, the actual proof on it is on page 706 in chapter 10 of my old calculus book, or you can look it up, the proof for the second derivative of parametric equations. You can Google that. But this is just like a simple version of it. If I start with this here, it's really this guy, the dx part there is squared. So, and when you put the 2 by the d there, it means do the derivative. So it's the derivative of dy and then 2 dx's like that. So it's kind of take the derivative with respect to d dx of dy dx. And then what they did was they changed this dy dx to dy dt over dx dt, which we know is true. So we're taking the derivative of that, which is pretty much like what we've been saying. And then they, if you have a fraction multiplied by another fraction, it moves, basically you can multiply the tops together and then the denominator just stays, this denominator is right here. And then all they did was just say then this is with respect, they kind of, if you look at these denominators here, they just switched them around. If you're multiplying denominators, it doesn't matter which order they're in. So they end up getting then the derivative with respect to t of dy dx and then put it over dx dt again. So the long and short of it is you have to do, when you're doing the second derivative, instead of just doing the first derivative and taking the derivative, you do the first derivative and you take the derivative. That's what this top part is saying. But then you have to divide it by the derivative of x with respect to t again. So that's the one thing that people forget. They forget to divide it by that thing again. So we'll talk about that more as we're doing some of them on here. So it's not a very long proof. It's just kind of a quick. There's a better proof on that other page if you want to come look it up. All right, so let's just do one here. So these are both, they've got t as our parameter here. T in this case is an angle on there. And it just says to find the first and second derivative. So our first thing is to do the derivative of this guy right here, of x with respect to t. So what's the derivative of dx dt here? What's the derivative of cosine of t?
Negative sine of t.
Negative sine of t. And you're doing this with respect to t, so it's not like you have an inner function or anything here. See, it's with respect to t there. And then we'll do dy dt, 3 sine of t. What's that derivative?
3 cosine t.
Right, 3 cosine of t. So our dy dx then is going to be the y coordinate, the y dy dt rather, over dx dt. Can that simplify? What's cosine over sine? Yeah, this is negative 3 cotangent of t. dy dx. Okay, so we have the first one there. The problem with this is it's with respect, I mean, you've got dy dx here. So you've got this derivative with of y with respect to x, but then you have a t in the equation. So you still have to deal with that t when you're doing this. You'll see that coming up too later. But if they just want an equation for it, if they just say find that, this is what they expect you to do. You don't have to put it into rectangular form. We'll just stay in parametric form. Okay, so now our second derivative, this is the one where people get messed up because they want to just do the derivative of this guy. But that's the top part. It says do the derivative again with respect to t of that, do d dt of dy dx. So that means do our derivative of this right here. We'll put it on the top. So what's the derivative of negative 3 cotangent of t? Derivative of cotangent is what?
Sine squared.
Nope. Derivative of cotangent. It's another trig function.
Not arcsine, second.
Yeah, secant. Cosecant, right? Derivative of cotangent is negative cosecant.
Yeah.
Remember that? You got to know those trig functions. Get them, refresh them again there. So it's our negative 3, but then it's times negative cosecant squared of t. Did I just say cosecant? I meant cosecant squared. Did I miss that squared before? Anyway. Okay, and then we have to divide it by the dx dt, which was this guy up here. So you've already got that part done. You just plug it in again, like that. Okay? And isn't sine just 1 over, cosecant is 1 over sine? Or sine is 1 over cosecant. So I could get this sine up onto the top as changing it to 1 over cosecant and then inverting it, and it ends up being then 3 cosecant cubed of t. Okay, there's our second derivative. All right. So these lessons, when I used to teach these after pre-calculus, they were actually a really short lesson because we didn't have all that stuff before, but makes them into a little longer lesson because I have to teach you the pre-calculus part too. This part is actually not that hard. It's pretty simple actually. So find the slope and the concavity of these. So slope is which derivative? First, and concavity is? Yeah, second derivative. So that's all they're doing, finding the slope and the concavity. It just tells you to do the first and second derivative. The difference here is they actually tell you a point to do it at. So we have another step where we're going to plug in that point on there. All right, so let's see. The first dx dt, see, x is equal to t to the 1/2. So what's dx dt? Right, and I'm going to, well, you could put it in the denominator or the numerator here. I'm just going to do it as this for now. Just leave it as t to the negative 1/2, but you could put it 1 over 2 square root of t if you want. And then our dy dt, go ahead and do that. There's our y there. So we end up with what, 1/2 t? Yeah, our derivative. So our dy dx is our y, dy dt, over dx dt. Okay, so the 1/2s here will cancel, and because that's a negative right there, I left the negative off, sorry. That's a negative on that. Now this can move up to the top as a positive, so we get dy dx is equal to t to the 3/2. Okay. Okay, do the second derivative. What do we do to do the second derivative then? Get your notation right too. The 2 goes in between the d and the y. And then it's out here on the end of the dx like that. What do I do first? What goes in the numerator? Right, the derivative of this guy. So go ahead and put that up there. 3/2 t to the 1/2. Power rule there. And then what goes in the denominator? Yeah, back here, this dx dt. So 1/2 t to the negative 1/2. So when I simplify that, it will become 3t. Just moving the t up as a positive 1/2 power and combining those, and then 3/2 divided by 1/2 is 3. Okay, so here's our second derivative. Have I answered the question? Not yet. Yeah, I haven't found the slope at these points. The problem is this is an x and a y. I've got t in my equations. So this is where you got to go back and you got to think, what would t have been in if this is my x and y? So I think about if x is 2, if I plug a 2 in here for x, what would t end up being? So if I go 2 is equal to square root of t, well, you square both sides, t equals 4, right? And you can check it by plugging in 3, the 3 for the y, into this y right there. And you'd see you get the same thing there. T is equal to 4. You actually get, I think, plus or minus 4 on it, but it tells you that t has to be greater than 0, greater than or equal to 0, so you know it's t equals 4. So you have to kind of, sometimes you have to take that x and y and figure out what t is based on it. Then you can plug it in here. So get your notation correct. On the last test, a lot of you lost I would say up to even maybe 5 or 6 points on the test because your notation is not what it is. So what it's supposed to be, what they look for. So when I'm doing things in class, you got to realize that's what you got to practice, okay? So you want to practice getting this notation. I'm doing this at the 0.23, or even better, now that I found out what that makes t, since I'm plugging in something for t, I would rather put at t equals 4 here. You could put the 2, they would both be correct, but I like putting what I'm actually plugging in. So either way is fine, and then you just plug in the 4 equals, whoops, I need my equal sign there, equals 4 to the 3 halves, or 8. So there's the slope at the 0.23. Okay, then we'll come over here to this guy, and we're going to do the second derivative at, whoops, I put the 2 in the wrong spot. There we go. At t equals 4, or at the 0.23, and that is equal to 3 times 4, which is 12. So that's my second derivative. Did I answer the question then? What does it say? Yeah, it says find the slope and then the concavity. So what's the concavity if this is a 12? It's positive. It's a positive concavity, so it's concave up. Remember, if it's positive, it's concave up. If it's negative, it's concave down. So you'd have to show all this work. Like you couldn't skip this step and just go, oh, it's concave up. You'd have to actually show that you got 12 there, and then that you know it's concave up. So now we have all of the work that's required on this. Okay, none of these steps can be skipped. Okay, you cannot skip this stuff. You've got to show all this work. Yeah.
So does it matter if you plug in the 2 or the 3?
No, I just plugged in the 2 because this equation here was easier. So I usually pick the easier one, and I plug in a 2 for x there and figure out what t is. It will be exactly the same no matter which one you do, because it has to be, because it was derived. That 0.23 came from plugging in some value, the same value of 2 into each of the equations. All right. Okay, let's try another one. So this time we're supposed to write an equation of a tangent line to the curve defined by x equals t minus 1 and y equals 1 over t plus 1 at the point when t equals 1. So don't get too confused on all of the different wording here. Just look at, here's my key thing. I'm writing an equation of a tangent line. So what things do I need if I want to write an equation of a line? A slope and what else? Right, you need a slope and you need a point. Slope and point. Well, you can get the point easily. You're doing this when t equals 1. Just plug in a 1 for each one of those t's and you'll get your point. Okay, so the point will be just plugging a 1 in there. What do we get?
2.
For the y coordinate, yeah. What about for the x coordinate? 0, yeah. So it's the point 0, 2. Okay, so that was pretty easy. Now to get the slope, isn't that just dy dx? The slope is just dy dx, so we are just doing our derivative there. We've got to do dx dt and dy dt, and then put dy dt over dx dt, and we'll have an equation for our slope. Okay, so let's see. The derivative of the x is just 1, right? And the derivative of y is just negative 1 over t squared, or negative 1 t to the negative 2. So you put the y over the x, and we end up getting just this guy, right? Because x is just 1. So it is negative 1 over t squared. Okay, so now let's do our dy dx evaluated when t equals 1, because that's where they said to do this at, when t equals 1, and plug it in, and you get negative 1. So now I have my slope here, and I have my point. We just write our equation. Y minus the y coordinate is equal to slope times x minus the x coordinate. And you don't even have to simplify it. If it's a long part of the answer, you can just leave it like that, whatever you want. Or if you recognize that that was a y-intercept, you could have put it right into y equals mx plus b, whatever you want. Okay, Let me see 5 to 0. Can you do the first and second derivatives and use them in problems like we've got here to find slope, concavity, equations of tangent lines? Everybody 5 to 0, where are we at? Awesome. Okay, so the last concept for the day then is arc length. So arc length is, remember, just you have some curve and you want to know how long a part of the curve is on there. Do you remember the equation that we had for arc length for rectangular coordinate? What was arc length on rectangular? Just a regular old x and y equation.
Integral from A to B,
Of what?
square root of 1 plus or minus, I think
It's plus, yeah.
and then f prime squared.
Very good. F prime squared dx. Right, don't forget that dx on the end there. So, and it came, I don't know if you remember that lesson or not, but remember we kind of did a little bit of a proof like on this. It comes from the distance formula, and it ends up simplifying to this, where you have this is like the difference of the x's squared, difference of y squared kind of thing. It was a long drawn out proof there, but it came from the distance formula. Well, look at this. Doesn't it look very similar to that? That's just the change of x. Dx dt is the change of x squared. Dy dt is the change in y squared. Square root of that. Isn't that the same thing as the distance formula? Because change in x is x2 minus x1. Change in y is y2 minus y1. It's just the difference between them there. They're just different ways of writing the distance formula. This is the distance formula right there, which comes from Pythagorean's theorem. Okay, so it's basically the same. They're very, very similar here. The difference is obviously you have with respect to t now instead of with respect to x on here. See how the integral ends in dt because we have t's in here now. So let's use our formula then to figure out this one. And we're going to start with, we have to find our dx dt and dy dt. So dx dt is just 1 here using these equations. And dy dt is equal to, what is that? Negative 1 over t squared. So we put them into our arc length formula. Is equal to the integral from a to b, and we're going from t equals 1 to 3. This is with respect to t, so we want to put those 1 to 3 on our lower and upper limits there. And then we have a square root of our dx dt squared, which is 1 squared, and our dy dt squared, which is negative 1 over t squared squared dt. Now you're going to have to use your calculator for that, just like when we did our regular arc length formula. Usually it's a calculator problem because it's very difficult to integrate square root of things that are addition in there like that. So basically you put it in your calculator and you should get 2.147. Okay. All right, now we could have done this another way. If I wanted, I could have eliminated the parameter on it. If I eliminated the parameter, I would have to go through all the work of eliminating it, like solving one of the equations, probably the x equation for t, and then plugging it into the y equation. I get y equals 1 over x plus 1 plus 1. So there it wasn't too difficult to eliminate the parameter. But then I'd have to think, I'm going from 1 to 3 on this, so I have to think if t is at 1 and at 3, what would my new parameters? This is now with respect to x. So it'll be a dx on our integration. So I need to know what the x's would be. So I just go up to this equation here. I plug in the 1 for t and I get a 0 for x. Plug in the 3 for t, I get a 2 for x. So I could actually now do my arc length as going from 0 to 2 and using this equation now back with my regular arc length for polar, or for a rectangular form, which is this one up here. Rectangular is just what we call our coordinate plane. It's just the plain old rectangular coordinate plane. And so we could plug in here the square root of, and we'd have our, in that formula it's just a 1 there always, 1 squared, or just a 1. same thing as 1 squared. And then do the derivative of this guy, so I'd have to do the derivative there. If you go through and you do your derivative, it ends up being negative 1 over x plus 1 squared. And we put that in here. And square that, and then do dx. Turns out, when you put this thing into your calculator, you get the exact same thing that you got before doing it using parametric. So this was a lot more work down here. So my point on showing you this is don't rely on, oh, I'm just going to go back to the rectangular all the time because I know those equations. Go ahead and still memorize this. It will save you time. The AP test is timed. You need to save time as much as possible. This was much faster doing it this way than it was converting it to rectangular and then using the rectangular formula. Okay, one last thing. One of the problems in the book, I think it's problem number 5, asks you to graph on your graphing calculator using parametric mode. So all you do is you just hit your mode button, go down to I think the 4th line on the TIs anyway says has function and then parametric and polar. It's like abbreviated FUNC and then PAR and POL. You just go down to that line and switch it over to PAR, which is parametric, and then when you hit y equals on your calculator, then instead of giving you y equals and you type in the functions with respect to x, it gives you x equals and y equals, and you type the functions in, and then when you hit the variable key, a t will be put in there instead of an x when you're graphing those. Then you just hit graph and you'll see the graph show up. I think number 5 ends up being an ellipse when you graph it. It's kind of interesting graph there. So let me know if you have any questions. Thanks.